creating, say, parthenogenic species. So I believe it, that one thing you see is eggs that have not undergone reduction, reduction in the number of chromosomes, and there are ways of actually activating development. Usually the fertilization of an egg not only brings two haploid genomes together into a diploid genome, I know this, but there's also a signal that is sent out that begins development. So I know you can actually sometimes signal development without actually having a sperm present. But beyond that, I don't know any of the details. But that's a good question. Yeah. No, it's remarks. I did ask them about this. You think maybe further north where it's colder, you'd see more females and males depending on whether it's a crocodile or a turtle or whatever. That's not the case. And it looks like these nest temperatures are pretty constant, and it could be also that the threshold at which they change sex can also evolve. But it is remarkably constant. And there's a body of theory that, population genetic theory that can predict sex ratios. It predicts equal investment in males and females is what it predicts. And so, there's got to be some genetic mechanism that determines how development occurs even environmentally when the triggers in the environment. There's going to be something that cascades that says, okay, you become a male turtle, you become a female turtle. But so that is, what are the genetics underlying that type of development, are subject to natural selection as well, so they can be changed. But yeah, I think it's remarkably constant. You don't see lots of males or females in the north or south. That's a good question as well. All right, so I want to, here's just an example of a parthenogenic lizard. I did a lot of chalkboard work these last two lectures, so I'm going to have the rest of this is going to be a keynote. And here's Daphnia, one of the sexually reproducing species, or sexual or asexually reproducing species. But what I want to do is turn my attention to something that's related to what we talked about, why we reproduce sexually, for instance, and talk about sexual selection. And here's the observation, and one, frankly, that is at odds with what I was telling you about natural selection through reproducing more offspring or survival, right? These are types of traits that you see in many species where males, so for instance, all those males on the right, have characteristics, features that seem maladaptive. So you look at a bright red feather, right? And I told you a lot already about mice in the desert, right? We know that natural selection can actually fine-tune the color of the coat to match the substrate, right? And here you've got birds flying around that have red feathers. I mean, isn't that maladaptive? Wouldn't predators more easily see the red feathers? Not only that, they are so long that they even hinder flight, right? So here's another characteristic of, you're telling me that natural selection favored that, right? How can you explain that? And the answer is sexual selection. This was an idea that Charles Darwin and Alfred Russel Wallace both came up with. And the point here is what I just said, that many species have secondary sexual characters that seem maladaptive. This is called sexual dimorphism, where the males and the females differ in traits. So what is the explanation? Well, the explanation is that these characteristics evolved to allow males to have more mates, right? And there's two different possible explanations, two different forms of this. So let me just show you some examples of sexual dimorphism. Here's the Hercules beetle. This is a male Hercules beetle, these big giant guys with big asymmetric horns. Here's a female, looks like a beetle, a little beetle. We're all probably familiar with elephants. The males have large tusks, the females have small tusks. Here's an extinct Irish elk that just had these outrageously long antlers. And then you're probably familiar with cases like in bighorn sheep where the males and females differ in the size of their horns. These are just examples of some secondary characteristics that males will have that females won't have. Here's another example which you're probably familiar with. Lions, you go to the zoo, lions, the males and females look quite different. The males have these big manes. They're also bigger animals, right? So the explanation, here's another example. There's lots of examples. Almost every species you go to that sexually reproduces, often the males and the females will be quite different. So here's the pheasants. You often see, once again, like in many birds, the males have these elaborate bright colors. And then the males have these spurs that they use to fight other males with, right? And then some of the males have these little tiny spurs. They don't fight as well. Yeah. Sure. Is that better? That is better. I can hear myself too, which is a little creepy. All right, so let's get down to the two types of sexual selection. So the idea for what drives evolution in these secondary traits is two not mutually incompatible explanations. One is it's male-male competition, and the other one is a mate, or usually a mate choice, usually female choice, or inter. So sometimes people call this intra, within a sex, versus inter, between sex selection. So I'm just going to talk about some obvious examples of male-male competition. There's a number of types. There's within group dominance. I'll give an example of that. But basically, this is the case where a hierarchy is formed through interactions among individuals. With the individuals at highest hierarchy have more access to mates. There's female defense polygyny, where you have a male defends a group of females from other males and mates with this group of females. There's territorial polygyny, where a male guards a territory, and any females that come into that territory mates with. And there's lekking. Usually, lekking, I'll describe that as a crazy system that some birds and other organisms have, but you'll have competition for position or lek. So let's go on to some examples within group dominance. This is one you're probably familiar with. So many canids, such as gray wolves or wolves, live in packs and groups. And within the group, there's a social hierarchy that is formed, usually through interactions such as this. Sometimes you can even see these interactions if you have more than one dog. Almost everybody will probably observe that one of the dogs always seems to win arguments, right? That would be an example of a hierarchy being set up in your home, right? The same sort of hierarchy is set up in nature, and the individuals highest in the hierarchy also are the ones that mate the most. Here's an example of female defense polygyny. These are northern elephant seals. What happens is that the females come to the beach, and these males will defend groups of females. And so often the males will engage in these really big battles. The loser will kind of slink off back to the ocean while the winner will stick around the beach and continue to mate with the females there. In these types of cases, the male typically is way bigger than the females. So and it makes sense. The males that are reproducing are the ones who won these fights in the past. Okay? As an aside, when I was an undergraduate, I was doing field work with David Lindbergh. So it was out in San Nicolas Island. I think it's one of the California Channel Islands. It's run by the Navy. But we were doing bird surveys along the coast, along the shore. And I was walking about one quarter of the island. So I was walking along my one quarter of the island, and just kind of had my head up in the sky because I was looking for birds right along the beach. And I heard this quarter sound like a toilet flush. And I started to look, and there was this big male elephant seal sitting on the beach. And the only thing I'd ever heard about these, because people had seen these, and it's like the last thing you want to do is get between the elephant seal and the beach and the water. And there I was between the water and the elephant seal, and I basically ran. And he, that was my, it's kind of funny to see them on this and say, okay, they're kind of, I don't know if they're not really cute, but there they are. They're not very threatening. But we actually see them up close. They're really large, scary-looking animals. Here's an example of territorial defense polygyny. This is an example with Impala, but this is a case where a male will set up a territory and defend that territory from other males. So here's an example of two males going at it. One is trying to maintain his territory, and the other guy is trying to take it over. And there's competition for good territory. You might imagine the females might wander into areas that have lots of food, as an example, right? So if you're a male, you don't want just any territory. You want the best territory, the territory that's going to be most likely to have females around. Here's another example: water bucks headbutting. There's even examples after mating called sperm competition. It's a little bit, this is once again male-male competition, but it's after copulation has occurred. So two males have copulated with the same female, the sperm fight it out for access to the egg. And there's, even within primates or even apes, there's a fairly large difference in how mating occurs. So in humans, of course, we're supposed to be monogamous, and presumably for the most part we are. But in chimpanzees, they are not necessarily. You can have one female will copulate with many males, and that sets up an ideal situation for sperm competition. You have sperm from different males in the female reproductive tract. And what you'll find in chimpanzees, especially when you compare them to humans, they have this really, really large testicles. It's probably because each ejaculate has so many more sperm, so they compete. And there's also lots of other things that the sperm can do. Some sperm will sacrifice themselves, form tangled webs that will try to block the competitors, allow some selective sperm from their own to go through. So it's actually really fascinating to think that you can even study male-male competition at the level of sperm. They call it sperm competition. So the next thing I want to talk about, so that's male-male competition. I think it's kind of, I don't want to say obvious, but I think it's, there are examples you're probably familiar with. Okay? The other type of sexual selection that occurs is mate choice. And it's almost always the females that are the choosy sex. So if you have a choice, you have to say, well, who's choosing, right? And the choosy sex is almost universally the female. Now there's two different broad categories I'll discuss. There's the resource-based explanations and non-resource-based explanations. But let's first go over why it's the case that the females are the choosy sex. Well, a lot of it has to do with anisogamy. The fact that the females are the ones that have the big gamete. So just from the get-go, the females invest in a lot more energy into an egg. And once again, you can't necessarily use your intuition for how much investment making an egg versus a sperm involves. You say, well, in humans, imagine the energy budget for formation of eggs in humans is pretty small relative to other things that females do. But in many species, the egg is a big investment. If you're very small and you're making a big egg, that's a large investment. Right? So don't use your intuition for what you think might be happening in humans to extrapolate that to all different species. And then just in general, internal fertilization carrying young to term is costly. We know that internal fertilization carries the risks of, say, contracting a parasite. We call them sexually transmitted diseases. And then something you probably are familiar with is that there's a bigger asymmetry in the amount of energy males and females invest in carrying an offspring to term. Right? So there's a big asymmetry. For a male, the cost of a sperm is nothing. For a female, carrying a child to term is a big deal. Okay? There are cases where the roles are reversed, that the males are the choosy ones. And in those cases, it's the case the male is doing something that's so costly that it outweighs the female investment. So a good example of that is seahorses, where the males, it's the female that's just kind of here are the eggs, I'll see you later, or actually I won't see you later, right? So they fertilize eggs. The seahorse male cares for the young and for a long time, so it's very costly. So the male seahorse is the choosy sex. But that's an exception to the rules. It's always the case that the female is the choosy sex. So why choose in the first place? There's a large number of explanations. I already gave you two broad categories, resource-based and or direct benefits and indirect benefits. But here's an example of some of the reasons. So there is this issue of mating with the correct species. Mating with the wrong species is a very costly mistake in terms of what happens. I'll discuss that later when we talk about speciation. It might be that if you're choosy, you might choose a mate that has better fertilization ability or higher fecundity. It might be that that your choice is influenced by what that individual can bring. You go, okay, fine, bring me food or bring some resources. A better nest, for instance. It might be that you choose based on your perception of the parental ability of that individual. It might be that that the individual gives you a better breeding territory or resource. Maybe the individual will confer lower risks or hazards. Or it might be that the offspring are somehow going to be better because you chose the right mate. That is to say, they'll have a higher fitness. So you're choosing in some way based on genes, how good the genes are. So let's go and talk about some of these direct benefits. Once again, these are the easy explanations. So direct benefits are things like you're a male, you give a gift, right? You provide some resource to the female. And so in bush crickets, they provide what are called nuptial gifts. Basically, it's a spermatophore, a protein-rich substance that the females can feed on, and these spermatophores are very, very costly for the males to produce. Actually, almost half of the male's body weight is in a spermatophore that it gives to the female. And if a female selects a male that provides a large spermatophore, she can have more young. She has more energy to produce more eggs. So there's a direct benefit to the female in that if she gets a lot of energy, a lot of food from this male through the nuptial gift, she can lay more eggs. So that's a direct benefit. The ones that are more difficult to explain and see are the indirect benefits or ultimate benefits. And there's a number of different possibilities. One is good genes. That is to say that in some way your mate choice, you choose a mate based on your perception that your children will have a better genes and be more fit and survive better. But this requires a number of things to be true. So the females in this case are going to choose a mate which offers good genes. These genes are going to have to influence her offspring's chance of survival. And the quality of that mate somehow has to be advertised. Otherwise, how could she choose? How could she distinguish between an individual who has good genes or bad genes? So there has to be some signal that she can recognize that indicates whether that individual has good genes or bad genes. Okay? And whatever that trait is, it has to be heritable. And there has to also be heritability in how good the mates are. As I say, some males have to be better than others for this entire system to work. And in some of these systems, some of these explanations, there's no cost to the secondary trait the male has. In other cases, there's a high cost for the male having the trait. So the ones where the male has a high cost, sometimes they're called the handicap model. The idea being, if a male can survive with a tail like that, he must have good genes. That would be kind of the explanation. It's a handicap. If you can survive and reproduce with a secondary trait which is so excessive, then you must be a good male. But there's, how much time do I have? Maybe I have some time. So there's some examples that have been tested out there. So this is a gray tree frog. It's highly versicolor. And what is the signal in this case? It appears to be the call length. So once again, you have to have some way for females to choose among mates. In this case, it's the call length. Some males have these short calls, and some have long calls. Actually, there's this fellow at the University of Texas by the name of Mike Ryan who studies these frogs, and he's wonderful at imitating the frogs. So you can actually, at this point, if I were Mike, I would at this point give you examples of the calls. I'm not Mike, I cannot do these frog calls. But anyways, there's long and short calls, and you can recognize them, and they're repeatable. So there's an experiment that was done to ask whether females that chose long call males versus long call males, short call versus long call males, had offspring that were better in any of a number of different measurable ways. So for instance, if a female chose a long call versus a short call male, was there a significant difference in larval survival? And the answer was no. There was no statistical difference between larval survival for these frogs if the female chose the long call or the short call. How about the mass, how big the tadpole was at metamorphosis, right? Was there a difference if the female mated with a long call or a short call? Well, no, there wasn't. How about time to metamorphosis? Well, in that case, there was a significant difference, and the females that mated with the long call males the offspring developed metamorphosis much more rapidly. And they did that in a high food environment. So the two different situations that they looked at the offspring in were when you gave the tadpoles lots of food versus just a little bit of food. They looked at two different circumstances. But you can see in this case, that anywhere you see LC is a case where there was a significant difference in that particular quantity. And notice it's always the long call ones that are better. You don't see some cases where short call was better, some cases where long call was better. It's always the long call. When the female mated with the long call males, there was some measurable, significantly different measurable trait in the offspring that was where the long call males were better, or the long call quads were better. Okay? Does that make sense? Okay. If it weren't the case, and you see, and there was significant difference, you might see FC and LC, short call and long call interspersed. So I'm going to stop there and talk about a few final topics on sexual selection before we move on.